There's an exercise on page 66 that's probably worthwhile. Let's start right here at standard atmospheric pressure is 1 atmosphere. I'd like you to report that in various units for absolute pressure, then for gauge pressure, and then for vacuum. So atmospheric pressure is 1 atmosphere. It's 760 torr, which is the same as 760 millimeters of mercury. That's 29.92 inches of mercury. It's 33.90 feet of water. It's 14.70 psi absolute, and it's 2,116 pounds per square foot absolute pressure. Now, gauge pressure is atmospheric minus 1 atmosphere. So the gauge pressure, when standard atmospheric pressure is 1, would be 0. So there's 0 gauge pressure. And the vacuum, third column, vacuum, well, the vacuum is 0. There's no vacuum at standard atmospheric pressure, right? Vacuum is how far you are below atmospheric pressure. Let's consider the case if you have 2.5 atmospheres. This might be in something like an aerosol can. You got a high pressure. Let's say the total pressure in the can, the absolute pressure, is 2.5 atmospheres. I'm just going to report those in terms of other units. 760 millimeters of mercury times 2.5 is 1900 torr, or 1900 millimeters of mercury. 29.92 inches of mercury times 2.5 is 74.8 inches of mercury. 33.9 feet of water times 2.5 is 84.8 feet of water. 14.70 psi times 2.5 is 36.8 psi. And 2,116 times 2.8 is 5292 pounds per square foot. Now the gauge pressure is 1 atmosphere less than what we have here. So 1 less than 2.5 would be 1.5 atmospheres. 1 atmosphere less is 1900 minus 760 is 1140 millimeters of mercury. Gauge pressure for 74.8 inches of mercury absolute would be 29.92 inches less than this, which is 44.9 inches of mercury. Gauge pressure for water in feet of water would be 84.8 minus 1 atmosphere is 50.9 feet of water pressure. And gauge pressure psi would be 14.7 less than 36.8 or 22.1. Gauge pressure in pounds per square foot is 5292 minus 2,106 is 3175. Now, we can't talk about vacuum when the pressure is greater than atmospheric. Vacuum refers to how far we are below atmospheric pressure. What happens at 0.6 atmospheres? Partial vacuum. Say you're doing a vacuum filtration. The total pressure inside the vacuum flask is 0.6 of 760 millimeters of mercury, and that's 456 torr. It's 0.6 of 29.92 inches. That's 18.0 inches of mercury. It's 0.6 of 33.9 feet of water. Total pressure is 20.3 remaining. 0.6 of 14.7 psi is 8.82, and 1270 represents 0.6 of 2,116 pounds per square foot. That would be the total pressure remaining if you're only at 0.6 atmospheres. Some of the atmospheric pressure has been removed. If now you measure the gauge pressure in the second column, right? Gauge pressure, we subtract 1 atmosphere from the total pressure. So 1 atmosphere taken from 0.6 is negative 0.4. So the gauge pressure is minus 0.4 in the Buchner funnel. 456 minus 760 is minus 304 torr, or millimeters of mercury. That's the gauge pressure inside the Buchner funnel. For 18 inches of mercury, minus 29.9, you'd wind up with minus 11.9 inches of mercury. So if you put a gauge pressure gauge on there that would measure negative values, it would read minus 11.9. And I'll show you some gauges that do read negative gauge pressures shortly. If we had 20.3 feet of water absolute, we subtracted 33.9, our gauge pressure would read negative 13.6 feet of water. 8.82 psi absolute, subtract 14.7 is minus 5.88 psi gauge pressure. And 1270 psf absolute minus 2116 is minus 846. That's what the gauge pressure would read. It's reading that far below atmospheric pressure. And that's what the vacuum is. The vacuum is how far are you below atmospheric pressure. So the vacuum in the first case would be plus 0.4 atmospheres vacuum, or 304 torr, or 304 millimeters of mercury vacuum. Or you'd say there's 11.9 inches of mercury vacuum. That's how far you are below atmospheric pressure. Or you can say you've pulled 13.6 feet of water vacuum. Or you can say that you have 5.88 psi of vacuum, or 846 pounds per square foot of vacuum. In the final case, let's go to absolute zero. Let's completely evacuate the flask, nothing left. So there's 0 atmospheric pressure in any of the units. Now you'll have a gauge pressure will read minus 1 atmosphere in each case, right? Because a gauge pressure reads 1 atmosphere below the true value, and the true value is 0. So it's going to read minus 1.0 atmospheres, minus 760 millimeters of mercury. It'll read minus 29.9 inches of mercury. It'll read minus 33.9 feet of water. And the vacuum in this case, how far below atmospheric is it? It's a complete atmosphere below vacuum. It's 760 millimeters of mercury vacuum. It's 29.9 inches of mercury vacuum. It's 33.9 feet of water vacuum. Those are terms that are used on gauges and in history. Now I have the answers to this at the end of the chapter. So if I went too fast, you can always check them there. It is not possible for an absolute pressure to be less than 0, right? Once you've completely evacuated it, it's 0. You can't have a negative absolute pressure. And it's not possible for a gauge pressure to be less than minus 1 atmosphere, right? Because gauge pressure is always 1 atmosphere less than absolute. If absolute is 0, then the lowest you can go is minus 1 atmosphere gauge. It's not possible for a vacuum to be greater than 1 atmosphere, right? Same deal. Once you've removed 1 atmosphere of pressure, you have 1 atmosphere of vacuum. You can't go any more than that. You can buy the most powerful vacuum cleaner in the world, but you still can't pull more than 1 atmosphere vacuum with it. Now you can pull at a higher rate. You can get a higher flow rate with a bigger motor. So there's something to be said for that. Higher flow rate might mean more particle pickup, but you can't improve on complete vacuum. The biggest pump in the world, the largest vacuum pump in the world, cannot pull more than 1 atmosphere of vacuum. Please take a look at page 67. I have an exercise for you to read pressure gauges. And this is very much what you would actually see on many gauges. Although you may see more graduations, you'd actually see this type of reading. And usually very little information is given, and it's expected by the manufacturer that somehow the reader, the user, would know how to read it. So I'm going to help you do that. So this gauge on the far left here is open to atmosphere. So we know that atmospheric pressure in inches of mercury, we'll just say 30 inches. So it's really 30, but it says 0. What's that mean? Well, this must be a gauge pressure gauge. It's reading the gauge pressure, not the true pressure, right? Gauge pressure is 1 atmosphere less. So the gauge pressure that it's reading is 0 inches of mercury. It's a gauge pressure gauge, and it's reading 0 inches of mercury. What's the true pressure really? If it's really open atmosphere, we know it's got to be 30 inches of mercury. And we get that from our formula as well. 0 gauge pressure plus 30 inches of mercury atmospheric. And the vacuum in this case, well, the vacuum would be 0 inches. You can't have a vacuum unless you're lower than atmospheric pressure, and we're not. Now we're connected to a lab vacuum. We're this far below atmospheric. This is 15 and 30. What's this about? Let's just say it's 10 inches below atmospheric. The gauge pressure is actually minus 10 inches of mercury. Gauge pressure measures the height above atmospheric. If it's below, it's a negative gauge pressure. Let's calculate the absolute pressure. Is the gauge pressure, which is minus 10 plus 30 inches for atmospheric. The absolute pressure is 20 inches of mercury. See the distance from here to here? This is absolute 0, so it still has 20 inches of absolute pressure left. What's the vacuum? Well, the vacuum would be plus 10 inches of mercury. The vacuum is how far below atmospheric you have. That's 10 inches. So now our gauge is connected to a lab airline. So that's 0, 15, 30, 45. What's the gauge pressure? Well, it's what it says on the gauge. This is a gauge pressure gauge. It's reading 15 inches of mercury. What's the absolute pressure? Well, it's 15 inches plus atmospheric, which is 30. So it's actually 45 inches of mercury. What's the vacuum? Well, we can't talk about vacuum if the pressure is greater than atmospheric. Vacuum only exists below atmospheric. All right, same gauge. Now we have it connected to absolute 0 pressure, full vacuum. Full vacuum, what's the absolute pressure? Well, it's 0 inches of mercury. What's the gauge pressure? Well, it's 0 inches minus 1 atmosphere, which is 30 inches. So that's negative 30 inches of mercury is the gauge pressure. And the vacuum is plus 30 inches of mercury vacuum. Right? So if you pulled 30 inches of mercury vacuum, the gauge pressure is negative 30. This would be 0 gauge pressure. It's below 0 by that much. All right, let's go back to a partial vacuum situation. Here we're reading about, well, let's see. If that's 0 and that's 15, I'm going to call that 12, maybe, something like that. What's the absolute pressure? Well, the absolute pressure is what's remained. So if this is 12, this must be 18. I'm going to call it 18 inches of mercury. That's the absolute pressure. That's my best estimate of it here. The gauge pressure is the absolute pressure. That's 18 inches minus atmospheric, which is 30 inches. So we're looking at negative 12 inches of mercury is the gauge pressure in here. And that's what it says, right? It says negative 12 if this was calibrated, and that's minus 15, minus 30. But often they don't show negative and positive signs on gauges. It's understood. You compare it to the 0. This is really what a gauge would look like. And you got to figure it out. What's the vacuum? Well, the vacuum is this much below 0, so that would be 12 inches of mercury vacuum. Notice that the mercury vacuum is the same as the gauge pressure, just opposite sign. And now we're back to atmospheric pressure. So if this is atmospheric pressure and it reads 0, then the absolute pressure must be 1 atmosphere, or 30 inches of mercury. The gauge pressure will be, well, absolute pressure minus 1 atmosphere. So the gauge pressure is 0 inches gauge. That's what it says. And the vacuum again is 0 inches of mercury. That actually looks like the first example, just turned around a little bit. All right, this last one here, the gauge is, here's 0, 15, 30 is 45. So the absolute pressure is 45 plus 30. This is 45 plus 30, must be 75 inches of mercury pressure. And the gauge pressure would be 75 inches minus 30 inches is equal to 45 inches of mercury, and that's what our gauge pressure is reading. And the vacuum, of course, is not applicable to this case. And again, these answers are listed in the back of the course notes. Please turn to page 68. So I have some photographs of gauges that I went around the labs and found and took pictures of them under various conditions. And in each case, I want you to write down the pressure, absolute, the gauge pressure, and the vacuum in every case. So if you look carefully, I give you some information and try and read the gauge. Can you believe this? This gauge does not even say what units it's measuring in. So the manufacturer assumes that anyone who reads it would know. What could it be? Look at the values. This is 0, and it says 30 vacuum, 30 pressure. Well, what could it be? Well, it has to be inches of mercury, because only inches of mercury is 29.9 inches of mercury is atmospheric pressure. And you can have 29.9 inches of mercury vacuum, or 30 inches, right? So it has to be. It's interesting that the manufacturer doesn't even label the gauge. They assume that you're going to know. So I'm going to help you learn that. All right, so in this first example, I'll do a few with you. This gauge is open to atmosphere, right? So what is the absolute pressure, the gauge pressure, and the vacuum that is indicated by this gauge? Well, you can see here's vacuum, there's a 0, and there's pressure. Well, if it's open to atmosphere, we know, and it has to be inches of mercury that it's reading because the number's 30. The true pressure has to be 30 inches of mercury. That's atmospheric pressure. It's open to atmosphere. The issue is it's the gauge pressure gauge, so it's set to read 0, so the gauge pressure is 0 inches of mercury. How much vacuum? Well, you can't talk about vacuum when it's atmospheric. It's only if it's below. They're here the same gauge, but now it's got some pressure on it, right? What's the absolute pressure now? Well, it's got, let's say that's 12 plus atmospheric. It actually has 42 inches of mercury is the absolute pressure. The gauge pressure is what it's reading, because it's a gauge pressure gauge. It's reading 12 inches of mercury. And of course, you can't talk about vacuum if it's under pressure. Let's try another one. Okay, how about over here? This is now reading in the vacuum section. So what's it reading? The absolute pressure is the amount remaining in here. So if we count between, what's that, 12, 14, between 16 and 30, that's 14 inches of pressure remaining. 14 inches of mercury is the pressure, the absolute pressure. The gauge pressure is reading negative 16 inches of mercury. And the vacuum is reading, well, how much vacuum? It's got 16 inches of mercury vacuum. All right, so you can finish up that page. It's the same gauge in each case. Look at the next page, page 69. Here's a gauge I found on one of the labs, and notice this one says absolute pressure. Kind of neat, tells us what it is, but it doesn't tell us the unit again. That's kind of interesting. So the manufacturer assumes we can figure out that it must be what? What is atmospheric pressure that has a unit of 15? Well, it has to be PSI, because 14.7 PSI is atmospheric pressure. So I'm going to say P absolute, because that's what it's reading. I'll just call it 15 to make it simple. 15 PSI. What's the gauge pressure? Well, the gauge pressure is absolute minus atmospheric. It'd be 15 minus 15. The gauge pressure here is 0 PSI. What's the vacuum? Well, the vacuum would be 0. All right, so I'm going to let you do these. I have a new gauge down here, but I've told you how it's connected, but you can figure out from this what kind of gauge it is. Is it absolute or is it gauge pressure? It says it's connected to an empty oxygen gas cylinder. Now when I say empty, I don't mean evacuated. I just mean what someone would say, well, now it's empty, nothing's coming out. So really it's connected to atmospheric pressure. So can you figure out what the pressure is, the atmospheric, the gauge, and the vacuum in that system? Here at the bottom of the page I have a couple more gauges. I think with enough information, see, it tells you absolute pressure, and outer scale says inches of mercury, and the inner scale says millimeters of mercury. So you can read those. Absolute pressure, right. On the next page I have more gauges with information on each one, and you should be able to figure out what the units are and what it's reading in terms of absolute, gauge, and vacuum, because that's the way it would be in reality. When you go to work, you're going to find some gauges that are just like these, and you need to know what they tell you. The answers to these exercises are at the end of the chapter, so check them out, please. I will certainly have one or two examples of a gauge on the test. Take a look at page 71, please. Mechanical pressure measuring devices. We've been looking at gauges. Well, often in the chemical industry we use liquid-filled devices to measure pressure. It's commonly done. And liquids might include water, mercury, brominated organics because they have a high density greater than 1, and sometimes you want a light fluid, so you'd use a hydrocarbon oil for low pressure measurements. We've already looked at the cistern barometer, called the well manometer. It measures atmospheric pressure because its well is open to the atmosphere and there's no pressure at the top of the mercury column here, right? The mercury fell down leaving a vacuum behind it. So it will stop falling when its pressure is equal to atmospheric pressure, so we can measure the height of the mercury, and that tells us atmospheric pressure. Qualitatively, describe the height of the mercury column in a tornado. Well, in a tornado, you have low pressure, so there'd be less pressure to support the mercury column. The column would fall lower and measure a lower pressure. During clear, cold weather, the atmospheric pressure is typically greater, so it would push the mercury column higher. If instead of being open to atmosphere at this end, the vented connection on this enclosed barometer could be connected to some enclosed vessel like a tank, then the barometer would read the absolute or total or real pressure in the vessel. Quantitatively describe the height of the mercury column when connected to a vacuum cleaner. So we connect here to a vacuum cleaner. Well, the vacuum cleaner will lower the pressure a great deal, so the mercury column will not be supported. It will fall very low. If you connect it to an aerosol can, then the aerosol can would push high pressure in and push the mercury column up quite high. Do problem number 2. Let's take a look at that. It's on page 82. On page 82, problem number 2 says the height of a mercury barometer is 76 centimeters. Okay, that's typical. Calculate the height in meters if oil of density 0.9 grams per milliliter is used instead of mercury. All right, start with 76 centimeters of mercury. The specific gravity of the oil is 0.9 because we're told the density is 0.9 grams per milliliter. In the CGS it's the same, right? That's for the oil. The specific gravity of mercury is 13.6. Now, will it take more oil, a taller column of oil, or a smaller column of oil, shorter, to exert the same pressure as 76 centimeter height of mercury? Think about it. I hope you say more, a lot more. It takes 80 kilometers of air, a column that high, to lift 76 centimeters of mercury. Air is much lighter than mercury. So mercury is the densest liquid. Anything else is going to take more. So let's make this number get bigger. Let's put the bigger specific gravity over the smaller specific gravity. Now notice how these units don't seem to cancel, right? Again, you can't cancel units when you use inverse relationships. And the density-height relationship is inverse. The denser the fluid, higher density fluids require shorter columns. Lower density fluids require higher columns to give the same pressure. So it's an inverse relationship. You have to use common sense here or memorize formulas. And I'm not giving you any formulas. I don't even know what they are. Just think about it. So if you work this out, that's 760 times 13.6 is 1148 centimeters. As meters, that would be 11.5 meters of oil. It would take 11.5 meters of oil to exert the same pressure as 76 centimeters of mercury. Of course, mercury's 13.6 times denser. No wonder we use mercury to measure pressure rather than oil for high pressure situations, right? We'd have the column is way too high to be usable. All right, that's number 2. Okay, back to page 71. We're looking now at a closed tube or J-tube manometer. So the cistern barometer we just looked at, right? It's an accurate instrument, but its large mercury well requires that it remain wall-mounted or otherwise secured. It's not portable. A more versatile, portable version of the barometer is called a J-tube or closed tube manometer. Well, it certainly looks like the letter J, doesn't it? So the well of mercury is replaced by a simple loop at the bottom, giving the manometer a J shape. So recall here this well of mercury. All right, so we can just replace that by this loop, which holds the mercury at a certain level. So picture, if you will, if I can draw this, as if this was a well manometer. Not going to fit, but this would be the liquid level in the cistern. And so it works the same way. We measure the height of mercury above the level of liquid in the well, or the level of liquid here in the J, and that height measured is the absolute or total pressure in whatever vessel it's attached to. So you can take this around with you in the plant and plug it into something and actually measure a pressure. And the pressure will be measured in units of H. Height will be centimeters or millimeters or inches, whatever it happens to be on the scale you're using. The same as in the cistern barometer. This is a vacuum, right? So there's no pressure here. The height of the mercury column indicates the pressure, whatever it connects to. And that's it. Very easy to use. I think there's a problem for us to do. Problem number 3. Let's check it out. Page 82. Problem number 3 says the height difference of a J-tube manometer is 26.2 centimeters of manometer fluid having a specific gravity of 10.2. Calculate the height difference of the manometer reading if the manometer fluid is changed to one with a specific gravity of 2.62. Right, so I quickly tried to sketch one here. Here's a J-tube manometer. The height difference is 26.2 centimeters of a fluid with a specific gravity of 10.2. What would be the height difference if the manometer fluid was changed to one with a specific gravity of 2.62? Comes back to the same question. If you had a less dense fluid, 2.62 is much less dense than 10.2. Would it be a larger column of liquid, or would it be less? Obviously, if you're using a less dense fluid, it's going to take a higher column of the fluid to exert the same pressure. So our delta H here will be 26.2 times the ratio of specific gravities to make it larger. So we're going to have to put the larger specific gravity over the smaller one. That's 10.2 Sg, whatever that stuff is, divided by 2.62 specific gravity. And that works out to 102 centimeters, which is like a meter high. Hard to visualize, but that's what the answer would be. Please take a look at page 72. There's a couple of principles that are fundamental to pressure problems that you need to understand, and it'll make solving these problems a lot easier. This is a gas syringe. So visualize, we pull the plunger back, so you collect 60 mils of air at atmospheric pressure, plug the tip with your finger, and then compress the plunger down to half the volume. Say you bring it down to 30 milliliters. So you've cut the volume in half, and then to do that, you've doubled the pressure. So if you plot that on a graph, you'll see you initially had 60 mils at 1 atmosphere. You dropped to 30 mils at 2 atmospheres. By doubling the pressure, you half the volume. Start over again with the plunger at 60 mils, and this time compress it down to 20 mils. So you've compressed the volume by a factor of 3, And you do so by increasing the pressure by a factor of 3. So the pressure will be 3 atmospheres at 20 mils. And one last time, starting with 60 mils at 1 atmosphere, compress the plunger in until you bring it down to 15 mils. You've decreased the volume by a factor of 4 from 60 to 15, and to do so you had to increase the pressure by a factor of 4. And that's called Boyles Law. It says that pressure and volume of a gas are inversely related. We'll need to know that. I suspect you do. The second principle we need to understand is this, that for liquids, pressures are equal at equal horizontal depths in the same liquid. I guess that's kind of obvious if you think about it. If this has a certain amount of water in it, and I'm talking about this depth, it has a certain pressure, I'll call it P1. If I move over here at the same depth, P2, these are equal because they have the same height of liquid on top of them. So for same horizontal depths in the same fluid, the pressure is equal. Has to be true. We're going to see that we'll be using glass tubes in which will be filled with liquids, water or mercury or some other fluid for measuring pressure. So these tubes are hollow, and let's just say I'm filling it with some liquid. If you pour liquid in here, and let's say they're open to the atmosphere, atmospheric pressure is the same on both sides. If you pour some liquid in one side, then the same pressure requires that this will level itself. These liquids will always level themselves and will always be at the same level. If you pour a bunch of liquid in this side here, that liquid will fall down and the other side will rise up. Eventually they're going to reach the same height. So if you look at a tube of liquid like this, it is always true that pressure is equal at the same level, the same horizontal level in the same fluid. Everywhere I'm drawing a horizontal line, this pressure is equal. So the pressure here is equal to the pressure here. The pressure at this point is not the same as the one below it, but it's certainly the same as the one horizontal to it. The pressure here is the pressure here. Right? Now, thirdly, for gases, pressure is essentially equal at any depth or height in a gas. If you have a column of gas, and we'll have that in some of our pressure measuring gauges and devices, you need to appreciate the pressure at any height in a gas is essentially the same. I'll say P1, P2, P3. Let's say P1 is equal to P2 is equal to P3. And I'm not talking about kilometers, I'm talking about feet or meters or inches of height. And the reason that's true is air is just so dilute that it takes kilometers of air. It takes 80 kilometers of air to contribute a single atmospheric pressure. So if you're talking about the difference between a gas at 1 meter to 2 meters high, the pressure is essentially the same, just as it would be in the atmosphere around us. 3 important principles we need to understand to solve pressure problems. So I think we'll stop here for this lesson and pick it up in the next lesson.